In this video lesson, we're going to take a look at nuclear half-life and the problems that you will be expected to solve regarding this topic. It's based on the stability of an element, and which we know from the previous lesson is dependent on the ratio of neutrons to protons in the nucleus. An element is stable when this ratio is 1 to 1, but can be stable at a ratio up to 1.5 to 1. That's a ratio of neutrons to protons. So it can have a 50% more neutrons than protons and still be stable, but anything outside of that ratio, atoms become unstable and are considered radioactive. Eventually, at a random moment in time, each unstable atom will individually, spontaneously decay by one of the 5 ways atoms exhibit natural decay that we discussed in the first lesson on natural radioactivity. Half-life, it's important to remember that half-life is time. It's a time that it takes for half of the atoms of a radioactive element to decay. We have a reference table M, that has selected radioisotopes. That's just short for radioactive isotopes. These are the elements. The nuclide is just the nucleus of the isotope that is radioactive. Half-life is a time. Notice the time is days or years or milliseconds or minutes, hours, right? So these are all units of time. Half-life is a time that it takes for half of these radioactive isotopes to decay by whatever decay mode that they are going to do. In this case, it's a beta particle. So this gold 198, if you had 100 atoms of these, after 2.695 days, 50 of those atoms will have turned into another atom. There'd still be 50 gold 198 atoms left, but 50 of them, half of them, spit out these beta particles and turned into a different, more stable isotope. Okay, so there's a lot of information here, from the name of the isotope to what kind of particles they're going to emit to how long it's going to take for half of those atoms to do so. Now, it turns out that the shorter the half-life is, the less stable it is, right? So these half-lives of, millions of years, right? We're talking about millions of years. Uranium-235, uranium-238, they are more stable isotopes. There are isotopes that, with a 7-second half-life, that is a highly radioactive. It's going to be decaying very rapidly, this nitrogen-16. Remember that the symbols, if we see a B+, that's a positron decay. There's only 4 listed here. Beta decay is symbolized with a beta symbol and a negative sign. There are 12 listed here. And alpha decay it's listed by this alpha symbol. There are 8 listed here. Okay, this is by no means an exhaustive list, but just to show you that predominantly we are looking at beta decay for the examples we'll be doing in our class. All right, so let's talk about graphing half-life and how we measure it. All right, we're going to be looking at radium-226. It has a half-life of 1,600 years, right? And so what that means is if we started today with 1 kilogram of radium-226, and then fast forward to 1,600 years from now, we would have only half a kilogram left. And if we let another 1,600 years go by, right? So this distance was 1,600 years. This distance, or this amount of time, is 1,600 years. And the third segment is the same. Okay, so if we let a second half-life go by, another 1,600 years, we're going to be down to only 1/4 of a kilogram of the original radium-226. And if we let a third 1,600 years go by for a total of 4,800 years, we are going to be down to 1/8 of a kilogram. Okay, so for every half-life that goes by, in this case 1600 years, half of the mass that we started with is going to remain, right? And so you'll notice that a half-life curve has this slowly decreasing curved appearance to the graph, right? So for radium-226 in 1600 years, half of the radioactive nuclei in the sample will change into new, more stable nuclei, which means that 50% of the mass of the radioactive nuclei in the sample will change into a new, more stable nucleus. We would measure it with using a Geiger counter whose count per time will be half of what it started with. Okay. So Geiger counter measures the particles that are being emitted, and we can study the rate at which those particles are being emitted, assuming that one particle gets emitted for every atom that decays. That is a very measurable way to determine the half-life rate. Okay. So let's talk about this, breaking this down mathematically. After one half-life, in this case it's 1600 years, 50% of the original amount of the sample will have decayed into a new element, and the other 50% of the original amount of the sample will remain as the original element. After two half-lives, in this case a total of 3200 years, right, now we are down to 75% of the original amount of the sample will have decayed into a new element, and we will have only 25% of the original amount left. After three half-lives, right, half of this 12.5% will remain as the original element, and a total of 87.5% will have decayed into a new element. This, of course, after another 1600 years for a total of 4800 years. The big idea here is that half-life time is constant for a given radioisotope. If a half-life time is 10 days, then two half-lives will be 20 days, three half-lives will be 30 days, four half-lives will be 40 days, and so on. All right, let's take a look, diving into the equation, the half-life equation. Looks fairly complicated. We're going to break this down and not necessarily have to be involved with a fractional exponent. But let's see what we are talking about. N as a function of T is the quantity of the substance remaining, where N sub 0 is the initial quantity of the substance. So the initial quantity, we're going to have to cut it in half a certain number of times, right? If we take that initial amount, we cut it in half a certain number of times, we're going to get the amount remaining. Okay. But the idea is I want to focus on this exponent right here. What does it mean? Okay. That exponent, T, the time elapsed, over the half-life of the substance, is going to be equal to the number of half-lives. And so we're going to really focus on using this equation just because the math, putting this into your calculator, can be troublesome for some students. So we're going to solve half-life problems. There's 4 types that you'll need to solve. 3 of the 4, you're going to be given a half-life time. Okay, this number right here. You're going to be given that for most of the problems. And of course, there's going to be problems where you're going to have to find that, but that's all right. We can do that. If I give you a half-life, and we know how much of the isotope we have now at the beginning, so we know the beginning amount, how much will be left after some time into the future? Okay, let's see a problem that looks like that. Half-life of zinc 71 is 2.4 minutes, right? So that is our half-life. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes has elapsed? Right, so this right here is the time elapsed, the amount of time that's gone by, and this right here is the half-life, right, because they tell us that's the half-life. So we know the time elapsed, and we know the half-life. From this, we can figure out the number of half-lives that have gone by. So let's start there. Time elapsed is 7.2 minutes divided by 2.4 minutes. Plugging that into your calculator, 7.2 divided by 2.4 is 3, right? So 3 half-lives have gone by. So that means we have to take our original amount of 100 grams and we have to put it through 3 half-lives, which means we're going to divide it in half. That's going to give us 50 grams. I'm going to divide that by half again. That's going to give me 25 grams. And we're going to divide that in half one more time because this was the first half-life, this was the second half-life, and this is the third half-life, dividing that in 2. That's going to leave me with 12.5 grams. So the answer here is that 12.5 grams of zinc 71 will remain. Get that on the screen, eh? And what that means is 87.5 grams of zinc 71 will have decayed or turned into a different element, which at this point we can't predict that because we, unless we were to go look up what kind of decay happened. Was it beta decay? Was it positron decay? Okay. So we could figure out exactly what that different element is, but that's not the point of these particular problems. Okay, now let's take a look at, again, you're going to know what the half-life is. Okay, but in the last problem, we knew how much we started with, and we had to predict how much we were going to get at the end. This time we're going to go backwards from that. We know how much we have now, but now going back, how much did we originally start with? So we have here osmium 182 has a half-life of 21.5 hours. So that's our half-life. We now have 0.125 grams of osmium 182 now, but how much did we have 64.5 hours ago? So this right here, 64.5, is our time elapsed. So we have half-life, and we have time elapsed. We're going to start with this equation to figure out the number of half-lives. Right? So the time elapsed is 64.5 hours. The half-life of 21.5 hours. Putting that into a calculator, lo and behold, that is 3. So 3 half-lives ago. So now, instead of cutting in half, we have to double it, right? Because we're now in the future, right? And we have to figure out what happened in the past. And half-life means it would have been doubled in the past for each half-life. So we're starting with the amount we have now, which is 0.152 grams. We're going to multiply that by 2, and we're going to get 0.250 grams. Taking that 0.250 grams, multiplying it by 2, obviously that's 0.500 grams. Taking that 0.500 grams, multiplying that by 2, it looks like we would have started with 1 gram, right? So the answer is we had 1.000 grams of osmium 182 at the start. Okay. Now, this third type, we don't know what the half-life is. We are trying to find out. So we do not know. We want to find out what the half-life is. So what we are going to do is rearrange this equation, because now what we're doing is trying to solve for the half-life. So if we rearrange that, that's going to be equal to the time elapsed divided by the number of half-lives. So to do that, let's see what we have in this problem. After 24 days, 2 milligrams of an original 128 milligram sample remain. What is the half-life of the sample? So time elapsed, we know that. We don't know the half-life, so we have to figure out the number of half-lives. To do that, we know the original quantity and we know the final quantity. So we can figure this out. 128 milligrams divided by 2 is going to give me 64 grams. 64 grams divided by 2 is going to give me 32 grams. And I lost a decimal point, I realize that, but we're just going to go with the math here to make it simple. So after so we've got one half-life going by, a second half-life going by, a third half-life going by. 16 divided by 2, it's going to give me 8 grams. That's the fourth half-life. We're trying to get down all the way down to 2, right? So 8 divided by 2 is going to give me 4 grams. 4 grams divided by 2 is going to give me 2 grams, right? So that was one. We cut it in half once, twice, 3 times, 4 times, 5 times, 6 times. So 6 half-lives. Okay, so that's the number of half-lives that's going to go in here. So our time elapsed is 24.0 days divided by 6 half-lives. That's just a number. That's not a unit. Okay, so obviously when we divide 24 by 6, we're going to see that that gives us 4 days. So the half-life of some substance, they don't even tell us what it is. The half-life, we're not even going to identify it because we don't know. The half-life is 4 days. All right, and the fourth type of problem, we're going to go back to knowing what the half-life is. So this is a known half-life again. But now we are going to figure out basically time elapsed. That's effectively what we are trying to find. Find the time elapsed. So radioactive dating, like you want to know how old a specimen is, and that specimen contains a radioactive isotope with a known half-life. So we are effectively trying to find out how long it takes for a radioactive sample to decay from a given starting mass to a given final mass. So bottom line, we're just trying to find the time elapsed. Here's a problem. We have selenium-83. It has a half-life of 25 minutes. How old is the sample? In other words, how much time has elapsed, knowing you started with a 10 milligram sample and ended with a 1.25 milligram sample? Well, if we have the starting mass and final mass, we can keep dividing by 2 to figure how many times we had to cut it in half, which is effectively how many half-lives happened. So 10 milligrams, divide that by 2, we're going to get 5. 5 milligrams divided by 2 is 2.5. 2.5 divided by 2 is going to give me 1.25 milligrams, right? So that is, we cut it in half once, we cut it in half twice, we cut it in half a third time. So 3 half-lives have gone by. All right. Now remember our equation. If we rearrange that original equation, I'm going to go back to it right here. Right. We're trying to find time elapsed. Right. Time elapsed is going to be equal to the number of half-lives times the half-life time itself. So that's where this equation comes from. The time elapsed is equal to the half-life times the number of half-lives. Okay, so the half-life time was given to us at this time, right? It has a half-life of 25 minutes. So 25.0 minutes times 3 half-lives happening is obviously going to be 75 minutes. So the answer here is that the specimen is 75 minutes old, which seems a little silly for practical purposes, but that's how you would go ahead and determine how old something is using radioactive dating. Now, practical uses for radioactivity. Radioactive isotopes are used to what is called irradiate food, right, which is to preserve it Food does not come into contact with the radioactive materials itself, but instead passes through the radiation beam, the energy beam basically, produced by the radioactive materials. It's ionizing radiation, which means that's radiation that can interfere with electrons in atoms, and that produces enough energy into the bacteria or mold cells in the food to break their chemical bonds, killing those pathogens, resulting in the food staying fresh longer. Radiation is also used in medicine to diagnose diseases as well as to treat cancer. If this is the case, the goal is to use radioisotopes that have a very short half-life and are quickly eliminated through the body or from the body in order to reduce risk to healthy cells. What we mean by being eliminated quickly from the body is that these are isotopes that would not get incorporated into your bone structure. These are isotopes that would not get incorporated into fat tissue. These are isotopes that would pass quickly through the urine and get out of your body very quickly. They have short half-lives so that if they do get stuck in your body, that they will quickly decay until they're stable and pose no additional threat to you. Some examples of radioisotopes that are used to help humans: carbon-14 is used to determine the age of biological remains, so that's a tool used by archaeologists. Iodine-131 is used to diagnose and treat thyroid cancer. So it's used to diagnose and treat thyroid cancer, because your thyroid uses iodine. It's one of the few places in your body that uses it, and this is why it's really important to make sure that the salt you consume is iodized salt. Cobalt-60 is a radiation source for cancer treatment. So when you hear radiation therapy, this is usually the gamma rays are coming from cobalt-60. So we'll say it's a radiation source for cancer treatment, otherwise known as radiation therapy. Technetium-99m is used to image blood vessels in the brain to detect tumors. Plutonium-239 is a fissionable fuel source for nuclear power or nuclear weapons. Americium-241 is used in smoke detectors. Americium produces charged alpha particles in a steady stream of alpha particles, and when smoke gets in the way, it interrupts the beam of those charged alpha particles, and when the beam is broken because of the smoke particles, the smoke detector sounds. Kind of a cool way to do that. Uranium-235 is a fissionable fuel source for nuclear power or nuclear weapons, and uranium-238, should have had a dash between there, is used to determine the age of uranium-containing rock formations, so this is often used by geologists. All right, in this video lesson, you have learned about practical uses for radioactivity, as well as different ways to calculate half-life problems, either given half-life or given time elapsed, or given starting and final quantities so you can figure out how many half-lives exist. Bottom line, a half-life is a time it takes for half of the atoms of a radioactive element to decay. Don't forget, you've got reference table N with selected isotopes in your reference tables. That is a very useful source for this topic. That's it for now. We'll see you back in the classroom.